Alright, so let's talk about the second part of DLSS, which stands for supersampling. So broadly speaking, supersampling is a type of anti-aliasing algorithm that's used in video games and also in other types of image processing. What supersampling strives to do is it strives to render an image at a higher resolution than is needed in the final product and then downscale or shrink the image. And the hope there is to gain extra image fidelity by doing that. It sort of works the opposite of when you blow an image up. If you take an image in, let's say, a PowerPoint, or even if you just use Photoshop and you don't do any fancy editing, if you were to resize an image and make it bigger, oftentimes you'll see that it gets more blurry or pixelated. It doesn't look as good as it used to in its original form. And the reason for that is you're essentially stretching the same number of pixels over a greater area, so the pixel density decreases by doing that. So it stands to reason that if you resize an image and make it bigger, you lose image fidelity. Then it stands to reason that if you do the inverse, you might actually gain image fidelity. If you start with a source image that's bigger than needed and shrink it, it stands to reason that the picture will look better. And that's exactly what happens with supersampling. So let's take a step back and analyze the motivation for why supersampling is even necessary. So many people probably are familiar with aliased and anti-aliased, but just in case, here are two pictures. On the left, you have aliased pictures, and on the right, you have anti-aliased pictures. So aliasing refers to these jagged edges. It's most noticeable on the circle on the left, in my opinion, where you can kind of see that the circle isn't very smooth. And on the right, the circle looks very smooth. It looks like a normal circle. And that's because the right images have some sort of anti-aliasing algorithm applied to them. If you zoom in very close, which is what the third row shows, the way anti-aliasing works is it actually has layers of pixels surrounding the actual edges of the image, and those layers of pixels increasingly get more opaque. And then when you zoom out, that actually fools our eyes into believing that it's a smooth edge, because at the end of the day, there are no such things as true curves on computer screens, because a computer screen is just a grid of pixels. But it turns out that if you're far enough away and you apply clever tricks like this anti-aliasing, you can fool the human eye into believing that it is a true circle. All right, so to try to make this idea of supersampling a little bit more concrete, I've gone ahead and tried to do supersampling my way in a very naive and simple way. So over here you can see the two sunglasses smiley emojis. So I drew these myself, and I want you to take a moment and try and guess which one is the supersampled one and which one is the regular one. So the one on the left is the one that's super sampled, and hopefully it's obvious by the fact that the one on the right, if you look at the edges of the circle, it doesn't look very smooth. You can see little bits of white popping in, and the reason for that is, so these images originally are 64 by 64. So for the one on the right, I had a canvas of size 64 by 64, and I just drew the circle as best as I could. It was really hard to do it. That's why the glasses look a little bit weird, the smile looks a little bit weird, because with just 64 by 64 pixels, there isn't much room to have that aliasing effect take place. So for the one on the left, what I actually did was I had a canvas that was, I think I did 256, no, I think I did 1024 by 1024. I drew the circle on that bigger canvas, and then I saved the image, and then I resized it to 64 by 64. And so then over here, I've taken the two images, I've blown them up a little bit so that it's even more obvious and exaggerated, the differences between the two. Obviously, they're not the identical images, and I'm not very good at drawing, so the circle on the right is a little bit squished, but hopefully the point comes across. All right, now that we've talked about deep learning and supersampling separately as disparate concepts, we're able to now bring them together and really discuss what's at the core of the Nvidia DLSS algorithm. And so, a little bit of a spoiler here, the crux of the algorithm is something called an autoencoder, which really combines the deep learning and the supersampling portions of the name. But before we define what an autoencoder is, let's see if we can just come to the solution ourselves. So let's start at supersampling. So to recap, we said that supersampling is the idea that we can render frames at a higher resolution than the final product will need, and then we can actually downsample or uh, shrink the image, and this actually increases our image fidelity. So that's akin to saying, let's render at 4K, let's shrink it to 2K, and the idea here is that our image quality will go up. But the problem, I guess, in quotes here, is that we're still going to be having an image that's 2K. It might look nicer, but it's only 2000 pixels top to bottom. But if I wanted to show this image or play this video game right on my big 65-inch TV, 2K might not be enough, right? I would want 4K or, in the future, maybe even 8K. So an enterprising individual might look at this and say, well, if I can go from 4K to 2K to make the image quality go up, can I just take something that starts at 2K and can I make it 4K? And so we briefly touched upon this, that the naive way of doing this is in Photoshop or in PowerPoint. If you've ever blown up an image, that's what this is. You take something that's small and you 200% it, and typically what happens is the frame becomes blurry. So most people have first-hand experience with this. There's no theory here. The image quality goes down. But what if we could actually do this without decreasing the image quality, or by not impacting the image quality so much? And that is the brilliance that DLSS brings to the table. DLSS manages to do something similar to this, where it blows up low-resolution images to higher resolution without impacting the image quality as much as a normal resize would do. So obviously, it can't make a 2K frame 4K and have that extrapolated 4K image be identical to something that's natively rendered at 4K, right? If it sounds too good to be true, it is too good to be true, right? So you do give up a little bit of image quality, but the power of DLSS is it's not as bad as simply resizing it naively. So what is this special resizing algorithm? So that's where this idea of an autoencoder comes in. This was the original motivation of making this video, because autoencoders are really cool. So an autoencoder is a type of neural net. So we talked about neural networks when we talked about deep learning. So an autoencoder, it's a type of neural net, a type of neural net. And actually, it's two networks sort of glued together. So it's two different computer brains. So if we think of neural nets as brains, right? So we have brain 1, and we have brain 2. What brain 1 does is it actually takes as input some image, you feed it to brain 1, and brain 1 outputs the downsampled image. So if we're looking at supersampling, if we go back to that and we think about this 4K frame, then this would be the 2K frame. Brain 1 compresses the input. This is then fed to brain 2. And brain 2's job is to try and guesstimate what this looked like originally. So we can actually say brain 2 will create something that looks very, very identical. I'm going to finish this off in a separate color to sort of show, like, it's going to be very, very identical to the original, but it's going to be ever so slightly different. And so this whole thing, this is our autoencoder. It is essentially a compression-decompression system where brain 1 compresses and brain 2 decompresses. And so if you've been paying attention, maybe you might have the sort of aha moment here that what DLSS is, at the end of the day, is your GPU is equipped with just this portion of the network. You're given Brain 2, and Brain 2 has been trained, like we talked about in machine learning, that there's the how and what, right? So if this Brain 2 is the how, the what is, it was trained on thousands, oops, oops, sorry about that. My mic fell. So Brain 2 and this whole network of Brain 1, Brain 2, they've been trained on tens of thousands of frame data. Um, and they've learned this very efficient encoding pattern. And you're given just the decoder part of this network. And that decoder part, or the decompressor, or the upscaler part, has learned how to take quote unquote lower fidelity images or lower resolution images, and it's learned to extrapolate them. So that's sort of it for DLSS. There's one more thing I want to quickly mention. The inputs actually to this autoencoder is a little bit more complicated than just frame data. So it's actually I'm trying to figure out how this works. Here we go. So if you remember, we had brain 1. The input to brain 1 is actually two things. We inputted a bunch of frames, so I'm just going to stack them like this. So we have a bunch of frame data, but we also actually give it sort of these motion vectors. So essentially what we do is we give it a frame. So let's say our frame looks like this. So we have person over here, and this is a player character, let's say, and you're pressing right on the control stick. And so your person is about to move to the right. So we pass it the frame data that looks like this. Maybe there's some clouds up ahead and there's a sun here. And then we actually also pass basically a vector field from calculus. It's essentially another image, you can think of it, of the same size as the original frame. But instead of the pixels and the image itself, inside this grid, we actually just have motion vectors. So essentially, where the person is, there'll be a little vector to the right. The cloud will just be a bunch of points because the cloud won't move. The sun will just be a bunch of points also because the sun isn't going to move this frame. And so essentially, every single point on the human, that character, is just going to be a little vector to the right. And this essentially helps the computer, or it helps the network, sorry, it helps our brain figure out what the next frame is going to look like. And so this is basically it. This is essentially DLSS. So I figured before I end this video, I'd try showing some real-world DLSS in action. I didn't spend too much time trying to get this perfect, but I did record myself dropping Fortnite twice, once with DLSS and once without. So here in this first clip, this is Fortnite 4K with DLSS disabled. So I hope it shows in the final rendered video, but there's basically frame stutter and sort of this lag that happens every, few seconds. It actually made me kind of a little bit sick while playing Fortnite at 4K with DLSS disabled. Alright, so over here we have another drop, and this is with DLSS enabled, sorry. And as you can see with the rapid motion, I was able to pan the camera back and forth, and I didn't get sick or dizzy. So there definitely was a noticeable improvement, I feel. Obviously, you can still see there is still a little bit of frame stutter, and it isn't rendering at 60 FPS, not even close, I think. But I do think that there was a noticeable improvement. And so that's that for DLSS. Please smash that like button or dislike button, I won't judge, and leave a comment down below telling me why you liked it or not. And as with the first part, if you notice any sort of oversight or correction, please do comment down below so that I can learn and people that are watching can also learn. Thank you for watching.